Welcome to another session of Circuits and Networks. In today's transient analysis class, that is class 12, we are going to see the basic problems which are involved with RLC circuit when the switch is open and the switch is closed. So these kind of problems we have already seen in our previous classes. Particularly here we are going to see the derivation as well as the solution of transient current for a given RLC circuit. Let us start with the basic problem. Here you can see we have 40 volts supplying 20 ohms, 4 henries and 0.05 farads when the switch is closed. And we need to find out the transient current. For this, we are going to start with the basic conditions. We know that the switch is open initially. When the switch is open, naturally no current will flow. And when current will not flow, it is understood that the value of developed current is 0 and developed voltage is 0. So that we are treating as at t equal to 0 minus, the current is 0 and the voltage is 0 just before switching. That is, the switch is not closed, the switch is open. So that is why we are treating this one as this just before switching. So for that, these are the conditions of current and voltage. Now, we know that the current through inductor and voltage across capacitor cannot change instantaneously. Therefore, as soon as the the switch is closed, the current will be 0 and the voltage will also be 0. Thus, the actual property of inductor and capacitor. With this, we are going to frame that the conditions of current and voltages are 0 before switching and just after switching. Then what happens if the switch is closed? When the switch is closed, the figure is shown in 1a. Now the current will flow and that current will be treating as transient current. Now once the current will flow into the circuit, what is the equation of current and how to obtain the solution for current is our main interest. For this, we'll look into the circuit and we are going to employ KVL to this closed circuit. I have minus 40 plus 20I plus 4 di by dt plus 1 by c, that is 1 by 0.05 integral idt equal to 0. So 40 change it to the right hand side of the equation and this becomes the actual equation of figure 1a. Now this is a general equation frame for the given circuit. Let us name this equation as 1 and I'm going to differentiate 1 with respect to t. Why like that? Because I need to find out the transient current. So it's a constant 40, so it becomes the value as 0. Derivative of constant is 0 and you have 20 here and you have I here, so this becomes 20 di by dt plus 4. Already there is a differentiation of one time and we are differentiating it with respect to t, so this becomes d square I by dt square plus differentiation of integration is I, which is equal to 0. I hope you understood how we framed this equation from equation 1. Now let me bring this equation into a generalized equation. So I'm taking 4 beneath of 20 and beneath of I. So this becomes d square I by dt square plus 5 di by dt plus I by 0.05 multiplied with 4. How we got 5 di by dt? Because 20 divided by 4 gives the value as 5. So this equation 2 is a second order differential equation. We can get the solution for this second order differential equation by taking the auxiliary equation from your engineering mathematics under BTech first year first sem. We can get the solution for equation 2 as d square plus 5d plus 5I is equal to 0. Now this d by dt is changed to d and hence d square I by dt square becomes d square. So I term is common, I am taking I common and thus we can frame auxiliary equation or also known as characteristic equation and we can reframe this equation 2 as equation 3. I hope you understood how we have framed equation 2 to equation 3. Now once we have done with equation 3, we need to find out the solution for equation 3. So I'm going to employ the formula for obtaining roots of given algebraic equation. So d12, the roots which are d1 and d2 can be obtained as minus b plus or minus under root of b square minus 4ac by 2 into a. I'm employing that. I have b, that is 5, and I have a as 1 and c as 5. So with this I'm going to get the value of d1 as minus 1.38 and d2 which is equal to minus 3.618. Now with this I am going to get the generalized equation as I of t is equal to k1 e to the power of minus d1 value, that is minus 1.38t, plus k2 e to the power of d2 which is minus 3.618t. Now this we are treating as equation 4 for the transient current which is obtained for t greater than 0. Now our interest is to obtain the value of k1 and k2. Once we are done with k1 and k2, then that will be the generalized solution for the auxiliary equation which is framed in equation 3. Is this clear? Okay. So how to find out the value of k1 and k2? K1 and k2 can be found out from the initial conditions. So from the initial conditions we know that I of 0 is 0. So in equation 4 I am substituting I of 0 as 0, which is equal to k1 e to the power of minus 1.38. Here t is there and we have to substitute the value of t as 0. So 0 plus k2 e to the power of minus 3.6180. With this I can get the equation as 0 equal to k1 plus k2. In fact, from equation 5 I can strongly say that k1 is equal to minus k2. I hope you have understood this step, how we have obtained equation 5 from equation 4, right? Now from equation 1, that is the generalized equation, that is 40 is equal to 20i plus 4 di by dt plus 1 by c which is 0.05 integral I dt, and the applying initial conditions I know that I of 0 plus is equal to 0. So I'm going to take I of 0 value as 0 wherever I have I. So I have 40 here plus 20, I is 0 plus 4 di by dt of 0 plus 1 by 0.05 integral 0 dt. With this I'm going to get the value of di of 0 plus by dt is equal to 10. Why 10? Because this value 20 multiplied to 0 is 0 and 1 by 0.05 multiplied to this 0 integral is 0. So di by dt of 0 plus which is equal to 40 divided by 4 will be value as 10. So this I am treating as equation 6. Once I am done with this, I am going to differentiate equation 4. Which is the equation 4? This is the equation 4. I of t is equal to k1 e to the power of minus 1.38t plus k2 e to the power of minus 3.618t. So this is the equation 4. So I'm differentiating equation 4. I'm going to get di by dt which is equal to, I have k1 and differentiation of e to the power of minus 1.38t is e to the power of minus 1.38t multiplied with minus 1.38. Similarly, k2 is a constant. Differentiation of e to the power of minus 3.618t is equal to e to the power of minus 3.618t multiplied with minus 3.618. Is this clear? Right. Now from initial conditions, that is di by dt of I of 0 plus which we got the value as 10, and from this above equation I am going to substitute the initial conditions with the present conditions. So I have di by dt of 0 which is equal to, wherever there is a t I have taken the value as 0, and thus I have framed this equation. And with this I know that di by dt of 0 plus is equal to 10. I am substituting a 10 over here, and e to the power of minus 1.38 multiplied with 0 becomes e to the power of minus 0 which is the value as 1. Hence I can frame this equation as 7. And I know that from equation 5 k1 is equal to minus k2, right? So I'm substituting the value of k1 which is equal to minus k2 in order to obtain the values of K1, K2. So K1 is 4.468 and K2 is minus 4.468. So we have done with K1, K2 values and we have framed equation 8. Just substitute K1, K2 in equation 4. So I'm going to get I of t is equal to K1, which is 4.468 e to the power of minus 1.380 minus K2, which is 4.468 e to the power of minus 3.618t. So this is the generalized solution for t greater than 0 and is known as the transient current equation. I hope you understood how we have obtained a general solution of transient current for given RLC circuit. Let us focus with the next problem. In this problem, you can see the switch is open initially, okay, and current is supposed to flow. When it is flowing, immediately the switch is closed. So before that, what is the conditions of current and voltages? And after the switch is closed, what is the immediate condition? And finally, what is the transient current which is flowing through inductor? That is our interest. So in this figure, it is shown that the switch was closed for long duration of time. Means what? The steady state conditions have reached. Means the behavior of the capacitor and the behavior of inductor in steady state conditions, they have obtained, they have reached, and then the switch is open. At that instant of time, what is the current and voltage across these passive elements? That is our interest. Okay, so we'll start with the solution at t equal to 0 minus, that is before switching, the switch is closed. In fact, if the switch was closed, in steady state condition, inductor acts as short circuit and capacitor acts as open circuit. And this we can imagine in the figure 2a. So this is how the circuit would have been before switching conditions. Means the switch was closed actually and then the switch is open. So when the switch was closed for a long duration of time, inductor behaved as short circuit and capacitor behaved as open circuit. And this is the circuit which have been obtained for steady state condition for long duration of time. So naturally, you can see the current which is flowing through inductor, it is obtained as I of 0 minus, whereas voltage across capacitor, it is obtained as VC of 0 minus. So what are these values? Since it's a closed circuit, so naturally the value of current will be 48 divided by 12, which is equal to 4 amperes. This you need to remember. And since the short circuit is placed parallel to the open circuit conditions, so naturally the value of capacitor voltage is 0. And we know from the behavior of inductor and capacitor that current through inductor and voltage across capacitor cannot change instantaneously. So naturally the value of I of 0 plus will be equal to 4 amperes and capacitor voltage will be equal to 0 voltage. So with equation 1 and equation 2, we have concluded with the initial conditions. Now our interest is to find out the transient current. So for t greater than 0, the circuit is shown in this fashion. The circuit is disconnected from the main source and inductor got charged and the current which is flowing through inductor is 4 amperes. So this is how we place the circuit, and that is connected to the capacitor which is connected to 5 microfarads. So this is the figure B of figure 2 which we have determined for t greater than 0. Right. Now we have to frame transient current with these two parameters. So I'm going to employ KVL to this closed circuit. What are the parameters we have? We have two, that is inductor voltage, that is L di by dt, 2 di by dt plus 1 by C, which is 5 into 10 to the power of minus 6 integral I dt equal to 0. This 4 amperes is flowing into the inductor, so that we are going to take as initial condition, and that is why we have not framed in the equation 3 about this 4 amperes, because inductor has already stored some energy. So naturally we have two parameters, that is inductor and capacitor, and that is how we have framed equation 3. I hope you understood how we have framed equation 3 from figure 2b. right? Now I'm going to differentiate equation 3 with respect to t, and I'm going to get, see here you have 2, just take this 2, bin it off, 1 divided by 5 to 10 to the power of minus 6. So 2 multiplied with 5 becomes 10, and 10 to the power of 6 goes to the numerator, it becomes 10 to the power of 6. In denominator you have 10, and numerator you have 10 to the power of 6. So this becomes 10 to the power of 5. And anyhow we have differentiated d square I by dt square plus 10 to the power of 5. Differentiation of integral is value is I, which is equal to 0, and thus equation 4 is framed from equation 3. Right. Now just find out the roots for this equation 4. So I'm changing it to the auxiliary equation. It becomes d square plus 10 to the power of 5 times I equal to 0. And I can easily obtain the value of d1 and d2, which is equal to 316.22j, and d2 is equal to minus 316.22j. So these two values I'm treating as equation 6. And for this kind of roots, we are going to get the general equation as I of t is equal to k1 cos 316.22 t. Here 22 value I'm negating, so that is why I have taken cos 316t plus k2 sine 316t. So this is the generalized solution for equation 5. To know about this topic into depth, you can go with engineering mathematics for BTech first year semester, where you can easily find out the partial differentiations and solution for the partial differential equations. From them, we have framed this equation 7. Anyhow, our interest is to find out the value of k1 and k2, and that can be obtained with the help of initial conditions. So this is our equation 7. I'm going to differentiate equation 7 with respect to t, and I'm going to see what I'm going to get. I'm going to get di by dt is equal to minus, since differentiation of cos is sine, that is minus sine. So minus internal multiple we have 316, so that is why minus 316 k1 sine of 316t, that is the differentiation of cos value, plus I have already k2, differentiation of sine is cos multiplied with the internal part of sine, that is 316. So this is how we frame equation 8 from equation 7. By differentiating equation 7, we got equation 8. Now from equation 2 and equation 7, that is, we know that the I of 0 value is 4 amperes. So I'm going to substitute the value of I of 0, which is 4, over equation 2. I'm going to get k1 cos of 316, t value is 0, plus k2 sine of 316, k value is 0. With this, I'm going to get the value of k1 equal to 4. How I got the value of k1 equal to 4? Because sine of 0 value is 0. So k2 term gets vanished. And I of 0 is 4 here. And k1 cos of 0 value is 1. That is how we got the value of k1 is equal to 4. And this I'm treating as equation 9. I hope you understood this simple mathematics. Now, from equation 3, we have 2 di by dt plus 1 by c integral I dt. So I'm going to take di by dt of 0. I'm dividing this 2 with the integral value. So integral of I dt divided by 2. So anyhow this value goes to 0. So it gives the value as 0. So di by dt of 0 is 0. This 2 multiplied with 5 will become 10. It's a small mistake over here. But anyhow it can be neglected because I of 0 value is 0 here. So this goes off. So di by dt of 0 is 0 here. And from equation 8, I'm substituting these the values of 0. So minus 316k1 sine of 0 is 0, plus 316k2 cos of 0 is 1, and already di by dt of 0 is 0. Hence the value of k2 becomes 0, and this becomes equation 10. So once I obtain the value of k1 and k2, I'm going to substitute to the standardized equation of 7. Then I'm going to get the value of I of t, which is equal to 4 cos 316t. So this is how we solve the problems which are involved with RLC circuits, especially pertaining to transient currents. I hope you understood this transient analysis class 12, which are involved with problems in solution of transient analysis pertaining to RLC circuit. Please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications. Thank you.